Welcome back. This is the second part of linear algebra in our book. This would be the algebraic view of linear algebra. What it really means in our context is that we will be trying to solve systems of linear equations. The first question we might want to ask ourselves is, when is it that we can actually solve linear equations? What are the solvability conditions? So let's try to take a look at that. Now, when you came across linear equations in your high school, or even before that, there must have been a statement that went something like, if we have as many equations as unknowns, we can solve them. Let's verify that. So we will take a very simple situation, two equations and two unknowns. X plus y equal to 5, x minus y equal to 1. By looking at it right away, you can know that just add these two equations, you get 2x equal to 6, so x is 3, subtract them, you get 2y equal to 4, y equal to 2. So perfect solution and no issues there. When you have an equation in x and y, you can plot it in what we will later call a coordinate space, a coordinate plane in this case. So we have one equation, the red one, the first one, x plus y equal to 5. So when y equal to 0, x equal to 5. When x equal to 0, y equal to 5, all good, it's a line. You just need 2 points, you can draw that. Then there's another one, x minus y equal to 1. So when x equal to 0, y is minus 1. When y equal to 0, x is 1. All good. So two lines, and they nicely intersect at this point, which is 3 and 2. And that is a solution. In other words, our red equation is specifying a statement of truth, saying that we are looking for x's and y's that add up to 5. All these points on the red line will add up to 5, so that is why that is a line. The second equation says that x minus y has to be equal to 1 as a statement of truth. Then you get a line. Then if you want to satisfy both of them at the same time, then you have to look at the intersection of these two lines, and that's where you get the solution. And there's only one unique solution. All very good. The reason why we could actually find a unique solution is because these two equations were independent and consistent. I haven't defined what independent equations are or consistent equations are, but we will do that later in this video. But for now, you can kind of understand what independent means. This means kind of like linearly independent vectors, kind of, not identical to. Consistency is a bit harder to define, but we'll see that. So that situation was an ideal system of equations. Now let's take a look at a non-ideal situation when we don't have enough equations. What if you have too few? These two unknowns, x and y, have to add up to 5. Then do we have solutions? Actually we do. It's just that it's not a unique point. It's the whole line of points, infinite number of solutions really, that will satisfy x plus y equal to 5. So again, give you a few. X equal to 1, y equal to 4, x equal to 2, y equal to 3, x equal to 500, y equal to minus 495, and so on. So you can choose any value of x, let's call it t. Then you just look at y 5 minus t, and that would be a solution. And that is actually a parameterized version of a line. For any value of x, you get a point in the line. Now let's take a different situation. So we have handled two situations. One was when the equations were independent and consistent, ideal situation. The second one, when you had too few equations, just one of them. Now suppose the equations are not independent. So this will kind of tell you what that means. It may look like you have as many equations as unknowns, but do we really have as many equations as unknowns? That is a question. So suppose you have x plus y equal to 5, 2x plus 2y equal to 10. So if you look carefully at the second equation, it is basically the first equation multiplied by 2. So the second equation is not independent, it's the same as the first equation. Now in this case, in the case of two variables, it's always obvious that the second equation, whether it is dependent or independent. But if you have three equations, then the third equation might be a linear combination of the first two, like 5 times the first equation minus 4 times the second equation. You wouldn't know by looking at it immediately that these equations are dependent or or independent. And if you have 5, 10, 50, 200 variables, then obviously it's not easy to tell whether the equations are independent. So in this case, the second equation really is dependent on the first one, and in reality you have only one equation. Is as good as having one equation. So again, you can choose any value of x, t, and y equal to 5 minus t will satisfy both the first equation and the second equation because they are the same equations. Now let's take a fourth situation where the equations are not consistent. Now you will see what inconsistency really means. So this will also illustrate the fact that it is not always true that if you have as many equations as unknowns, you can always solve them. It's not always true. It will give you two equations here, x plus y equal to 5, x plus y at the same time equal to 6. So you can see that right away they are not consistent because x plus y cannot be equal to 5 and 6 at the same time. So there are no solutions. But let's take a look at the shape of that in the coordinate space to understand why it is that you cannot actually solve them. So I have x plus y equal to 5 going through the points 5, 0 and 0, 5. And then I have another equation, x plus y equal to 6 going through 6, 0 and 0, 6. And these are parallel lines and they will never intersect. So there's no single point in this universe where these two equations are true at the same time. That's why there's no solution. So in this case, inconsistent equations are parallel lines. Now suppose you have another situation where you have too many equations. You need only two good equations, but suppose I give you 3. But again, it may look as though you may have too many equations, but we have to verify. Here's the system. It says x plus y equal to 5, x minus y equal to 1, 3x minus y equal to 7. Are there really 3 equations? The solution turns out to be the same as what we had in the beginning, x equal to 3, y equal to 2. And let's just substitute x equal to 3 and y equal to 2 in this equation. So 3 times 3, 9 minus y2, 9 minus 2 is indeed 7. So that equation is satisfied. Now my claim is that this equation is not independent of the other two. How do you know? I can tell you how in this particular case, the third equation looks like it is the first equation plus 2 times the second equation, x plus 2x, then you get 3x, y minus 2y, you get a minus y, so these two guys are okay. And now 5 plus 2, 7. So the third equation really is the first equation plus 2 times the second equation. And that's the reason why you could find a solution. Again, looking at it in the coordinate space, you have that equation, x plus y equal to 5 as before, x minus y equal to 1 as before, and you have one more green equation and green line now. It just so happens that it goes through the intersection of the other two. So these 3 lines have a point in common, and that would be a solution. That point, the coordinates of that point will satisfy the red equation, the blue equation, and the green equation, and that point here, that is the solution. We saw that these 3 equations were not independent. The third equation was just a linear combination of the other 2 equations. I'm using the term linear combination kind of loosely here because these are not vectors, these are equations. But later in your linear algebra life, you will realize that I'm justified in using that. Now, if you have too many equations, but they happen to be inconsistent, let's see what happens. So in the last instance where we had too many equations, the last equation, the third equation, was actually derived from the other 2. So it was consistent, though not independent. So the solution was a single point because there were really only 2 equations. The third one was derived from the other 2. But if the last one is not derived from the other equations, then let's see what happens. So these 3 equations, remember in the last case, we had the last equation was the first equation plus 2 times the second equation. The expression, the left-hand side is still the first equation plus 2 times the second equation, in which case the right-hand side had to be 7, but we're changing it to 9. So that introduces the inconsistency. Inconsistency basically means that these 3 equations cannot all be true at the same time, which you can see by looking at them in the coordinate space. And I can give you the punchline right away. There will be no solutions. So the first equation is before, x plus y equal to 5. Second one, the blue one, x minus y equal to 1. And the green one now instead of 3x minus y being 7, which went through this point, now it is offset by some number of units. 3x minus y equal to 9. Now, there's no single point of intersection for these three lines, so there's no solution. But can you still kind of say that there might be a solution? Some point inside this triangle formed by these 3 points might be a solution. Intuitively, you might think that maybe it's a centroid. Might be some point in there that might be the best possible solution. It's not a solution, it's not on any one of the lines, but it's the best approximation to the solution to all 3 equations. This is the best we can do. Woman-chin Leela. This kind of idea is actually what drives linear regression. It is not really the centroid, it's something else. Why it is different from the centroid comes from the fact that when you look at these 3 equations in a different fashion, one of them looks like it is more important than the other 2. It will turn out that it is the green equation, and the reason is that, roughly speaking, it is steeper, but it will come out kind of naturally in a different view. Right now, we don't know. Now, the best we can say is that there is no solution because these 3 equations are inconsistent, but we might want to keep in mind that even when there is no solution, we might want to come up with something that is the best approximation to a possible solution. Now let's kind of summarize what's going on here. So in the first case, we had 2 equations. They were very nice, pretty looking equations and a unique solution. Very good. 2 independent and consistent equations. Then you had only 1 equation in the second case. There you had an infinite number of solutions. It is wrong to say that there are no solutions. There are infinite number of solutions in this case. There's only 1 equation, 2 unknowns. The system is not constrained enough to give you just 1 unique point. The third case, it looked like you had 2 equations, but the second equation was just a multiple of the first equation. Again, you have an infinite number of solutions. The reason is that really you had only 1 equation. The second equation was a fake one. In the fourth case, the equations were inconsistent. The 2 equations could not be both true at the same time, so there was no solution. The fifth case, we have 3 equations, but the third equation was not independent. It was derived from the other 2. So the situation was the same as the first case, and we had the same solution, unique solution. The sixth case, which will turn out to be the case that you will have in data science most of the time, you have too many equations, 3 equations in this case, and they're not consistent with each other, so there's no solution. Even then, you will want to ask yourself what's the best possible approximation to a solution that you can come to. So summarizing in just 1 sentence, what they told you in high school or middle school or wherever it is that they told you this, life is much more complicated than the statement that if you have as many equations as unknowns, you can always solve them. It's not true. The closest thing we can say to this statement is something like, if we have as many consistent and independent equations as unknowns, we can uniquely solve them. That is probably the best thing we can say. If not, it depends. So as you can see, even for the simplest of possible cases, just 2 very simple equations, life was a lot more complicated than we might have anticipated. What that means is that when you start getting bigger and bigger systems of equations, say 200 variables, 500 equations, there's no chance in hell that you will be able to tell by looking at the equations or doing any kind of algebraic manipulations by hand whether they are solvable or not. We do need an algorithm. We need to put those things on a computer and then solve. That algorithm is called Gaussian elimination. Now, before going to Gaussian elimination, let's try to generalize the situation from R2 to Rn, because that's the game we play in linear algebra. So we have R2, then we will extend that to R3, and then to Rn where n is more than 3. Suppose you have only 1 equation in R2. What do you get? You get a line. So we saw that x plus y equal to 5 was a line going through the points 0, 5 and 5, 0. But even simpler than that, x equal to 0, that's the y-axis. But if you go to R3 and say the same thing, x equal to 0, then it's not a line, it's a plane. It's the yz plane. On the yz plane, x is equal to 0 everywhere. So it's a plane of points. And similarly, if you have a complicated equation like x plus y plus z equal to 5 or something like that, it will still be a plane. It's just that it'll be kind of angled with respect to the axis, and it might be shifted somewhere. Extending in Rn, what you will have is going to be an n-1 subspace. Why n-1? Because in R2 you had an 3-1 subspace, which was a plane. In R2 you had 2-1 subspace, which was a line. So similarly in Rn, you can imagine that is going to be n-1. It's not a point, so an infinity of solutions. Now if you have two independent and consistent equations in R2, those equations will define two lines and there will be a unique intersection. In R3, what's going to happen? You will have two planes. And what kind of intersection can you have in two planes? Well, if they are oriented with respect to each other, there's going to be a line of solutions, infinite number of solutions. If they are on top of each other, well, they cannot be on top of each other because they are independent. Similarly, in Rn, what you're going to have would be n-2. So as you can see, each equation is kind of taking away one dimension. To call it one dimension might be misleading. Let's call it 1 degree of freedom. So it's like taking away 1 degree of freedom from your space. So in R2, you can imagine that there are 2 degrees of freedom. You can go along the x-axis or the y-axis. If you have one line, then you're constrained to go along that line. So it has taken away 1 degree of freedom. In R3, taking away 1 degree of freedom, you will get a plane of points. In Rn, you will get n-1 subspace if you took away only 1 degree of freedom. But if you took away 2 degrees of freedom, then you would get an n-2 subspace. n-2 in R2 would be a unique point, a zero-dimensional entity. In R3, that would be still a line, so infinite number of solutions. If you have three independent and consistent equations, can you have that in R2? You cannot. They can either be independent, in which case they will be inconsistent, or they can be consistent, in which case they will not be independent. This cannot happen. But in R3, it is possible to take away 3 degrees of freedom and then you get a zero-dimensional entity, an entity that cannot move anywhere. That would be a point and that would be a unique solution. In Rn, when n is greater than 3, n-3 subspace, still an infinity of solutions. So you can increase the number, n independent and consistent equations. It cannot happen in R2, neither can it happen in R3. But in Rn it can happen. You have accounted for all degrees of freedom, then you have a unique solution. Now let's start looking at bad situation, non-ideal situations. You have two independent but inconsistent equations. In R2 what you have would be parallel lines, no solutions. In R3 you will have parallel planes, again no solutions. In Rn it will be parallel subspaces similar to parallel planes, parallel hyperplanes or something, still no solutions. Three independent but inconsistent equations. In R2, they can form different kinds of shapes. One that we saw was that the points formed a triangle, but it could be two parallel lines and one line cutting them, or three parallel lines. All those things are possible. In R3, the situation is similar. In the cross section, you might have something like a triangular tube. So one plane, one equation, another plane, another equation, third plane, another equation. This is going to make something like a prism, and any cross section of that will be a triangle. Or you could have three parallel planes or two planes with one cutting across, but no common points and no solutions. In Rn, of course, it's much harder to visualize, but no common intersection, no solutions. In R2, if you have n independent and inconsistent equations, again, it'll be similar to what you had in the case of three independent and inconsistent equations. It's just that you have more of them. R3 also, similar situation. Instead of a triangle, you might have a triangle and an extra plane somewhere, or a plane cutting the triangle, all kinds of permutations. But in Rn, of course, it becomes much, much harder to visualize, but no solutions. So summarizing the generalization, we can kind of define independence. Equations are independent if one equation cannot be derived from the rest by doing something like linear combinations, as we did in the case of vectors. Consistency is a kind of a cyclical definition by saying that an inconsistent system of equations is one that has no solutions. That's the best we can do at this point. The thing to realize is the number of independent equations in a consistent system of linear equations can never be greater than the number of unknowns. But what is kind of clear is if a system has more independent equations than unknowns, then it is necessarily inconsistent. So if you have three unknowns and five equations, and we say that these equations are independent, then they cannot be consistent. There are only three unknowns. The largest number of independent equations you can have would be three. That would already define just one point. And if there are more equations, if they are independent, then they have to be inconsistent. When we put these things in matrix lingo and look at it, you will see what that means. Later today, it will happen. So let's look at the matrix form of equations. Clearly, since the situation is so complicated, even in the case of just two variables, we need an algorithm to actually handle this. And that algorithm is Gaussian elimination. It works on matrices and it's specified in terms of row operations, but you have to cast your system of linear equations in a matrix vector form. So this is what we will do. Suppose you have m equations and n unknowns, then you will define a matrix that will be just the coefficients of the equations that you have. That is called the coefficient matrix. There are m equations, so there are m rows in this matrix. N unknowns, so there are n columns. Now x is the number of variables, that is n, and that also would be the number of columns of the first matrix, so that you can multiply with x, which has the number of rows as a number of variables. Then what's the size of b? B is the right hand side of each equation written in a matrix form. So there are m equations, so it will have m elements. So B is in Rm. So to say this once more, A has m rows equations and n columns variables, and those variables are in X, so that is in Rn, n variables. B, being the right hand side, the constant side of equations, will have as many elements as the number of equations, that is m, so B is in Rm. So A would be called the coefficient matrix, B will be the constants vector, so Ax equal to B, remember it is expression equal to constant, so Ax is the expression, B is the constant. So we have cast our equations in the form of a matrix vector product equaling a constants vector, all good. So next video you will see Gaussian elimination.